So in our last discussion, we kind of proved that U converges to T, what do you call, psi as T goes to infinity. Okay? So a natural question would be that at what rate U of T is converging towards C actually. Okay? At what rate the U of T is converging to C of T, or you can say mathematically that at what rate this difference of the norm is reducing, it's decreasing actually. Okay? So now we would like to answer this question in the form of the corollary that what is the decay rate. Okay, so what is the decay rate for this? So let me formulate the corollary and then prove the result. So the corollary is like this. So if theta is 1/2, okay, and this theta is same as the theta in Hejevich-Simon inequality and the inequality that we proved in our last discussion, then the rate at which the difference between U and psi is decreasing is exponential actually. So in other words, it's C naught times e power minus C1t. So in other words, U of t is converging towards psi exponentially, at an exponential rate, and hence the difference between them is decreasing exponentially. And if theta is between 0 and 1/2, then the rate of decay of the norm, or the difference between U and psi, is less than or equal to this function actually, 1 plus t power minus theta over 1 minus 2 theta. Okay, so it's decaying at this rate. So this is what that we would like to prove. So here's a little proof. Okay, so we know from the last lemma that we proved that the norm of ut is equal to norm of u plus u minus u cube, and this is bigger than or equal to, what do you call, some constant times exponential of u minus exponential e of psi power 1 minus theta. Okay, so this is something that we proved in our last two set of discussions actually. Now let me compute y of t, and let's call y of t as what? As e of u minus e of theta power theta minus 1. Okay, that will be power theta. Let's call this y power theta actually. Okay, so let's introduce a variable e of t, which is this, not e of u, but e of psi. Okay. Now let's compute dy by dt. Okay, we have already computed the derivative of it in our last discussion. So let's do it quickly again. So this is going to be theta times e of u minus e of psi power theta minus 1 times the derivative with respect to e of u minus e of psi. Okay. Now I know about psi that it's time independent. So the derivative of e of psi is going to be 0. I also know that the derivative of e of u with respect to dt is this minus u square t. Okay, so this is also a known fact actually. So this means I can, on this place, I can substitute this value. Okay, so if I substitute this value and say, let me write minus on other side, So the dy by dt will become theta times e of u minus e of psi power theta minus 1 times norm of ut square. But let me write the norm of ut square in this manner. So I'm going to write 1 ut, and on the place of other ut, let me put this. So ut multiplied by this norm, the plus u minus u cube and this norm. Okay? And for this norm, I know that this is bigger than or equal to constant times this quantity. So I can say this side is bigger than or equal to theta times e of u minus e of psi, okay, power theta minus 1 times constant times e of u minus e of psi power 1 minus theta and the norm of ut. This is what that you're going to get. You can clearly see that these two powers are opposite, so you can cancel them out. And what does follow from now here is that minus dy by dt is bigger than or equal to theta times c times norm of ut. I can call this theta times c as again constant c. So this equation dy by dt bigger than or equal to this can be written as dy by dt plus c times of norm of ut less than or equal to 0. Okay? Norm of ut less than or equal to 0. Or I can write it in another manner. I can take this constant and divide it on other side. Okay? And I can say that ut is less than or equal to negative 1 over c times dy by dt. Okay, that's what you're going to get. Keep in view that c times theta, I have again called it c actually. So if I now integrate the both sides from t to infinity and say t to infinity, okay, this will become what? This side will become minus 1 over c y, okay, say if you're integrating with respect to tau, so it's going to be y of tau evaluated at t to infinity, okay, t to infinity. Now as say tau goes to infinity and t goes to infinity, it doesn't matter. As t goes to infinity, what is y of t? So as t goes to infinity, this is my y of t actually. Where is y of t? This is my y of t. As t goes to infinity, the u of t will converge to psi. And hence, e of u converge to e of psi. So as t goes to infinity, y of t will converge to e of psi minus e of psi, which is 0. So y will go to 0. Okay? And when you're going to substitute, say, the lower limit, so this will give you what you call minus multiplied by minus, so it's going to be 1 over c y of t. Okay? 1 over c y of t. So I hope this is making sense to you. And this guy is bigger than or equal to t to infinity, ut, and maybe you can keep it as dt actually. And we also did this in our last discussion that I can estimate this by the norm of u t minus psi. So in other words, this norm is less than or equal to this integral, which is less than or equal to y of t. So that's one important conclusion that you have to keep. Now I'm going to show that for theta, so this is true in general. Now I'm going to show that for theta equal to 1/2, the y of t is basically this expression. So how can I show it? So this is the way to show it. I'm going to use this expression. Okay. Now if I know that my y of t is e of u minus e of psi power theta. Okay. Then what I can say? So I can say now that I can say now what? I can say that if I take, for example, power of y of t as 1 minus theta by theta, this will become e of u minus e of psi power 1 minus theta. So this will become the side of it actually. Okay? This is what the side of the equation will become actually. Okay? And now if I say that if I use this expression in this inequality, especially on this place, okay, what will happen? So I can say that my ut is greater than or equal to, it's greater than or equal to c times of y power 1 minus theta by theta. Okay. But from this inequality, I know that ut, so we proved it actually, that c times ut is less than or equal to minus dy by dt actually. Or I can say my norm of ut is less than or equal to minus 1 over c multiplied by dy by dt. So in this inequality, I can put, for example, minus 1 over c dy by dt. Okay? And for example, if I multiply the constant c on both sides, this minus 1 c on this side, and again call it c, then my equation, and take this dy by dt onto this side of inequality, this inequality will become dy by dt plus constant c times y power 1 minus theta by theta, and this is less than or equal to 0. Okay? This is less than or equal to, what do you call, 0. Now, so these are the two interesting inequalities that you always have to keep in head. One is this inequality, okay, A, and let's call this inequality B actually. Okay, let's call this inequality B. So this is true in general for any theta. So now let's take particular. So let's take theta to be 1/2. So if you're going to take theta to be 1/2, you will get dy by dt plus c times of y power, what do you call, 1 minus 1/2, so this will become 1/2, and this will become 1/2, so this will become cy less than or equal to 0. And I can easily solve, what do you call, this inequality by, say for example, multiplying the both sides by integrating factor and simplifying. In other words, the solution of this inequality, you can easily deduce that the solution of this inequality is that y of t is less than or equal to, your required constant actually. So it's e to the minus some constant t. Okay, some constant, what do you call, t actually. Now once you have this, so the solution of this inequality is this. So what you can do this, that on the place of y of t, now use this y less than or equal to minus c of t in A. So once you're going to use this y less than or equal to minus c of t in A, what you're going to get? You will get your required inequality, which is u of t minus psi is less than or equal to, okay, 1 over c, let's call this constant c naught, times e to the minus ct, let's call this constant c1t. So you have the first inequality. Okay, so this is your required first inequality when your theta is 1/2. Now I would like to do the general case. So consider the case when theta is between 0 and 1/2. So this would be a a bit involved case. We have to do deal with a generic argument actually. Okay, maybe we have to use some kind of comparison principle. So consider. So you have this differential inequality. Consider an inequality. Consider a differential equation that is not inequality, but it's equality actually. So the dz by dt is equal to. So in other words, it happens most of the time. If you want to solve an inequality, you equate it to equality and then solve it, and from that you try to deduce the solution for the equation. So let's consider, for example, in differential equation dz by dt equal to c times of 1 minus theta by theta equal to 0, and the z of 0 is equal to c of y of 0. Okay? Then this is simple linear equation type. You can do the integration factor, multiply both sides. You know how to solve the differential equations. So after solving this differential equation, your solution z of t that you're gonna get is really it's going to be c1 plus c2 times t power minus theta over 1 minus 2 theta, where the constant c1 is y of 0 power 2 theta minus theta, and the c2, this constant c2 is 1 minus 2 theta upon theta actually. Okay, c2 is c times of 1 minus 2 theta upon theta. So this is what is my solution of this differential equation. And now consider the difference between z and y. Okay, z is the solution of this equation and y is the solution of this inequality. And let's see that what is their difference. I want to prove that their difference is bigger than or equal to 0. So let me say that w of t is really z of t minus y of t. Okay, z of t minus y of t. So if I can prove, that my w of t is bigger than or equal to 0, then this is going to show that y of t is less than or equal to z of t, which I know explicitly. So I know this explicitly. And I know that 1 over c times of y of t is bigger than or equal to u of t minus psi. So if I can show that w of t is greater than or equal to 0, then I can deduce that this difference is less than or equal to some constant multiplied by this expression as required actually. Okay? So this was the strategy, the comparison principle that I would like to use. So w of t is z of t. So one little exercise for you is to show that if w of t is z of t minus y of t, then the dw by dt, dw by dt is going to satisfy an inequality, which is that this is greater than or equal to c times of f prime of some xi times w, or maybe plus of this bigger than or equal to 0, where, so in other words, if w is this, so you must verify, I'm not getting into the detail, that w satisfies this differential inequality. Okay, then w satisfies this differential inequality. Obviously, you have to use dz by dt and you have to use dy by dt. Okay, and from that you have to deduce this. Where and The initial condition is obviously going to be W of 0 equal to 0 because Z of 0 is Y of 0 and obviously Y of 0 is Y of 0. Okay? And f prime of this xi function is really 1 minus theta divided by theta, okay, times xi power 1 minus 2 theta by theta, where xi is some quantity between y and z. Okay? It's some quantity between y and z. Xi is between y and z. I don't know that whether y is big or z is bigger. Okay, from now. So xi is between something between y and z. Now, I can easily solve this inequality. Okay, in other words, I can take this inequality, multiply by the integrating factor, and you know how to solve, for example, differential equation of this form actually. Okay, this is not difficult. So what you can see that for this you will so if dw by dt satisfy this, then the following inequality would be true. So w of t multiplied by the integrating factor, which is 0 to t c times of f prime of xi of, say, tau d tau, and this is greater than or equal to 0. Okay, so this is the integrating factor that you can, if you're going to multiply it with both sides, then you can write them in a compact form. You know how to solve Leibniz linear type equation. The same strategy would work here actually. So this is bigger than or equal to 0. Now if this is bigger than or equal to 0, now either the both of the, so when the product of two quantities are both greater than or equal to 0, so either both are positive or both negative. But this guy cannot be negative actually. So this means that this is positive. So if this is positive, this must be positive as well. So W of t is greater than or equal to 0. So if the W of t is greater than or equal to 0, this implies, okay, that Z of t is greater than or equal to Y of t. And as I said, if the Z of t is greater than or equal to Y of t, then I can say that 1 over c y of t is less than or equal to z of t, which is this function, 1 over c times c1 plus c2 t power minus theta over 1 minus 2 theta over 1 minus 2 theta. Okay, and I know that this guy from my previous analysis, this guy is greater than or equal to u of dot t minus what do you call psi. Okay, and hence I can call this constant as constant c, and you get your inequality. So this is what is the proof of the rate of what do you call decay rate of this norm actually, or the rate at which the u would converge to psi. So I hope the calculations are making sense to you. I have left some gaps for you, so you have to fill it for yourself. Thank you.